The following is a conversation with Alex O'Connor on machine intelligence, creativity, and much more. Alex is a senior manager of data science and machine learning at Autodesk, who works building agile teams and impactful machine learning systems. Hey, it's Nono, and this is the Getting Simple podcast. Okay, welcome, Alex, to the Getting Simple podcast. The first thing I'd like to know is how long have you been working with machine learning? Because for me, this is a fairly recent thing. Maybe I started 5 or 6 years ago to take a look at this. How long have you been looking at this?
So thanks for having me on, first of all. I really appreciate it. I have to say one disclaimer before we go any further is that anything I say here is just purely representative of my own individual views and has no bearing on what my employer or other sponsors may or may not think. So anyone who's listening today, take it with that level of grain of sand. But I'm really excited to talk about everything that's going on, and it's an exciting time to talk about machine learning. It's interesting. My first kind of awareness of machine learning was in the context of undergraduate studies in computer science and computer engineering. And, at the time, I think it was machine learning was an interesting novelty that was a trick that people could do with software, but there wasn't really this understanding of the importance of machine learning in the future. And to me, it was something that I arrived at slowly over time as it became a tool that was the right way to achieve the goals that I wanted. And, early on, I guess my first awareness of it was in like the late 90s, but really I began to practice it and get really involved in it in the early 2000s, or 2008, 2009.
How has it changed since then?
Well, it's not a toy anymore, right? Like at the time you had neural networks, you had genetic algorithms, you had support vector machines, you had a lot of those sorts of things out there. And I think, there were specific environments where it was thought to be a useful thing to use. And there were definitely places where value was being generated, but it wasn't the predominant attitude that, this was going to be that, data-driven intelligence in software was going to be the predominant way in which we kind of, develop future technologies and the way we develop future work. And I think that really the most, the inflection point that was most obvious to me was when people started doing Bayesian classification of spam emails. Because for those of us who are old enough to remember the pre-Bayesian spam filtering days, spam was a real problem. And I mean, it's hard to imagine these days how much of a problem it was, but it was a threat to email as a communication channel. And this understanding that a naive Bayes classifier, which today is 2 lines of code, was enough to get a really high quality spam classification filter made was a real, I think, inflection point for a lot of people on this journey towards understanding that manually writing all of our logic was not going to be the way we would build software in the future.
Could you break down a Bayesian classifier?
Really, the key thing about it is that it's a supervised classification tool. So you have a pre-existing set of labels of evidence of your data points. So you have a collection of several thousand data points. In this case, it was whether your email is ham, as they say, a real email, or spam, meaning unsolicited commercial email, meaning scams, meaning all those sorts of things that were undesirable and polluting the inbox. And by showing a sufficient number of examples of these spam and ham email bodies to the classifier, each time you run it through the training, it would learn the properties of a real email from an unreal one, and at a high level of confidence and with a high degree of effectiveness.
What is used today to do this same task?
You can still get quite far with a very simple model, but I imagine these days they are using much more advanced deep learning models, probably using a lot of also structural information. So one of the things that begins to happen is the people generating the spam are increasingly trying to get around those filters. They're going to change what they do. They will alter things. They will attempt to poison classifiers. So you'll sometimes see a lot of very legitimate looking things coming through that aren't obviously spam. That's to try and, degrade the quality of the overall classifiers. It's a bit like kind of distracting the guard at the post. But, the more, I'm sure it's deep learning models, and I'm sure it's increasingly looking at things like the patterns of where the email's coming from, the traffic from them, the path to it, and those sorts of things as well. So at some point, purely the body alone loses its sole purpose.
Yeah, I'm surprised because there's still a lot of email spam, right?
Yeah.
A lot compared to what we know, but it could be really, really worse. And I imagine, if there was somebody at a company building one of these systems to protect against spam, they would have all the tools to build a spam generator that knows how to break through those rules, right?
Yeah, absolutely. And, I think there are structural ways that people have addressed that. There's this thing called, I think it's called SPF, which is a sender protection tool. There's a lot of increasingly network level pieces of analysis that get done to avoid that high level kind of task of just identifying someone who's going to do spam because they are going to release millions of messages at once. So if you see someone pop up, suddenly email millions of people all around the place in a very kind of systematic way, well, that's probably someone, the analogy might be if you're standing on the street and you see someone try every front door, they're probably not up to best intention, and similarly, I think there are methods like that, the network level.
Yeah, I can think so. I have, I develop websites, right? I normally use the same system, and I have already a logger installed, right? Something so you can visualize easily the logs on a web browser of what's going on, what errors you're getting, what 404s pages were not found. And one thing that's super interesting is how many tests from bots there are to retrieve environment key files or configuration files from WordPress or from common systems. And you look at them and say I don't have WordPress. Why are these people trying that? They're just brute force trying in many different domains the same techniques, because probably we could get a probability, right? Out of every 1,000 sites, there's 3 that are going to have this or that vulnerability. And what they're trying to see is if you've manually configured something wrong and you've exposed that your environment variables to the database URL, port, and password are exposed, or some other details, they just do that automatically and gather data that way.
There's an interesting paper a couple of years ago about understanding the intention of low quality spam messages. So they're somewhat unconvincing things where you get the kind of classic spam is hello, my rich relative has died and they happen to have the same name as you. There's $10 million in an account. I need you to come and impersonate this person for me to pretend to be that. And you sort of think to yourself, what rational person would even fall for that trick? To some extent, that's one of the interesting things is they don't want to trick smart people, right? Because smart people are going to figure out the scam or potentially report them, or potentially the likelihood of them continuing on the scam is low. So you have this interesting threshold where what they want to do is find people who are either desperate or who are, gullible or greedy in some sense. And in doing so, part of the objective is the same with these kind of tools that are searching, right? You want to find people who don't know to not put admin as their password, because those people are less likely to be running log analysis or less likely to understand that their site has been hacked. So, there's a sort of an interesting, it's like the analogy, I think, is you're trying to find the weakest zebra, right? You don't want to fight the biggest, strongest, heartiest zebra. You want to be the lion who catches the weak one at the back of the pack, because that's the one you're most likely to be able to catch and feast on most effectively. And so there's the whole game theory of why you choose these very these kind of messages that to an expert user are obviously fake, but to a less expert user might be deceptive, is part of the reason of doing that.
Also, it really depends, because I think at some point I've fallen into some type of scam. I don't know how much, but there's this case where, for example, I signed up on one of these vacuum robots.
Oh yeah,
right. Somebody had added a fake service authenticator through Google Home, right? You can register your own services, and somehow I found myself writing my email and password a few times and then say this might not be legit, right? So it's not only let's say non-savvy people. It can be I'm a developer, and in the right conditions I can fall under. And the easiest technique to protect against that is at least don't use the same password everywhere. Even if you have one
absolutely
number, or I always talk about algorithmic passwords. It can be the simplest rule that you can think of Like even like computing like how many letters this domain name has, and then you add that to the end, right? So something that protects you from automated hacking or something like that.
So circumstantially, there are definitely ways that you can be tricked. There's no doubt about it, but those have a lower probability, right? Because there's a more circumstances have to align for you to be in that situation, right? Like it may happen that it has happened to me. I've been waiting on a package and a fake FedEx spam has come through and I've been close to falling for that, you know? And so same thing, like at the moment, one keeps getting through my Gmail filter is invoices for a large big box electronics store support subscription. And it makes sense because again, that's the sort of thing that someone who might like very reasonably have and not really understand what they're paying anyway, because these are these long-term subscriptions that appear in the background that you buy with a piece of consumer goods. And it just happens that you know, the number is very large on it because the idea is that you go, oh my God, this bill is 10 times what I thought it was going to be. I'm going to ring these guys immediately. You're annoyed, you're stressed, you're kind of, and that switches off the kind of analytical part of your brain that says, oh, hang on a second, why did I get this bill? And why doesn't it look exactly like the one I got before? You know, so there are different ways to lure people out, and that's I think the same with the phone scams, where you have the ones where people pretend to be the IRS or pretend to be.
I got one of those ones.
Yeah.
They were calling my parents' house with an Indian guy.
Yeah,
was like faking that he was really mad and. Sir, you have your computer in front of you. Please don't laugh. Like you're taking this. You're not taking this seriously. Or,
yeah.
And I mean, you get also a bit scared because you say, okay, is this just like a regular call, or they actually have some information going to try to use it against me in some way, right?
Yeah, absolutely. Yeah. And I mean, it's interesting. You know, they those can be problematic because those people can decide they want to make your life difficult. They can set you on an auto ring for 24 hours, and they just like make your phone unusable, you know?
There is a complicated dynamic there because now the other day I had to cancel a credit card and I was calling them, and due to security and data privacy, they can't expose any of my personal details, right?
Yeah.
So they were asking for all the information from me, but I was thinking like, can you give me some data so I know that you're legit and I just didn't Google like a scam page or something for this number?
Yeah.
So they have, that's why service pins are super useful. Like they give you a pin in the contact center or something, and they say, okay, you give us the pin or we'll give you the pin. There's like a two-way verification that it's you who is calling and that the service you're calling is also legit.
Yeah, it's a second factor is a good one. The other joke is, that like the answer to your mother's maiden name is, purple one monkey dishwasher or 1 2 3 4 5 6, because you don't actually use, you have those, they use those secondary factor, personal information questions, but those are easily Googleable, or if you have a Facebook account, probably inferable from a small number of hops. So apparently, like, the advice there is if you are going to use those, don't give the real values, give something like spurious.
Yeah, like I always was thinking, what's the point of like using your birthday anymore?
Yeah, exactly. Yeah,
say, precisely. How old are you? Oh, when were you born? Are you?
Yeah, no, I mean, because, most people have a Facebook account, most people have, or something like that will reveal that information. Nothing withstands sustained surveillance, right? That's the truth of these things. Mostly what you're trying to do is protect against that, as you said, that kind of mass trolling where they're trying every website or every username, or they have 50 million usernames and passwords from a data breach. That's the sort of thing I think you're mostly trying to avoid, rather than someone determinedly trying to break in,
And you never get information from the attacker. Like if you get an email from Microsoft saying that somebody's trying to sign up with your email or something like that, you just get a verification code. It's like, this is a verification code that you have to use, but you don't know whether it's somebody that made it by mistake or if they're purposefully trying to break into your account.
And I have a few friends. I mean, it's you do see that. I don't know about you, but I have a couple of friends who have email addresses that must be similar to people who have similar names to them, and they type the wrong one in. And the net result is that they get people's invoices and stuff. I got signed up. I got signed up to Domino's in the UK by someone who used the wrong, and it was clearly a mistake because it was a legit person just ordering pizzas once a week. And it's just that I got the email saying, your pizza's on its way. Okay. So there was and it was a real Domino's thing, because I got in touch with them through another channel. Like I did that thing of go to the Domino's website, find the number, don't take the thing, don't click a link on the email. But Yeah, that was actually very difficult to resolve because they were like, well, we don't have any other contact details for this person. How are we going to? And privacy means they couldn't release who it was or any more information. And I was like, well, like, this guy, I hope he enjoys his pizza, you know?
Yeah. My dad's email got once this verification code that somebody was trying to sign up to PayPal.com.
Oh, yeah.
And the result was that, they couldn't sign up because the code was on my dad's email, but they had added a US phone number.
Oh,
right?
yeah.
So the thing is, like, on the chat, I tried to tell them, oh, there's somebody who's trying to sign up with this email, with this phone number, but this email is my dad's. And that basically locked completely that email because that guy couldn't sign up and my dad couldn't sign up anymore because the verification code now would go. There was something like you had to, what was it? Like you had to use a verification code that would get to that phone number or something like that. So it's basically like if somebody else tries to sign up in a website with your email, it might get locked for that person, but also for you.
Yeah.
So I don't know. It's a bit of a loophole. And going back to machine learning, right? These techniques have also been used in modern machine learning architectures to try to fool the network. So for example,
Yes.
in classification, I've seen like noise maps that completely make a classifier return a given label, right?
Yeah,
like a cat or like a zebra or something. And you actually can see noise, so you don't see any images. And so do you know anything about that?
Yeah, sure. The analogy I always like to think about is if you ever look at clouds and see a dragon or a panda, that's what you're trying to get the classifier to do. You know, it's sort of looking at the image, and to the human eye, it looks nothing like, really nothing like the thing that we're seeing. But more importantly, actually, more interestingly, are the ones where you mix the noise with a real image. So you have a picture of a panda, or you have a picture of a dog, and you mix enough noise into the image so that to a human eye it's completely undetectably different, but you can pick whatever model you want. What's interesting about that is the techniques. There's the white box, black box, and gray box, right? And basically the difference between the techniques comes down to what access you have to the classifier you're trying to attack. So with white box, you have the classifier on the table. You imagine it being like you can kind of test every value. You can like fit the parameters to the training directly. And black box is the opposite. You have no idea what's behind the interface. You're kind of adjusting it by hand. And in looking at the papers, what can be interesting in looking at the kind of work is to understand which level of access to the models you have, because for a lot of people offering these sorts of things, that's the key thing you want to kind of identify as your access, you know? I do think it's less obvious to me where these applications of these sorts of challenges, these adversarial attacks, as they call them, come up in classifiers. I mean, the applications for it are not as clear as they might be. One cool thing that you do see is people will print themselves t-shirts or face masks that will fool a face detector. But they're mostly fairly model specific. So you have to know you have to have a pretty good idea which model you're thinking of. And they're not pose invariant. So, they might work much the same way the face detectors kind of don't work, at different angles of your face. You'll find that it's hard to create something that does all round 360 view. But that's kind of the most interesting application of that I've seen. You have it though as well in any model. Because a machine learning model, what it essentially does is compress the input into a decision manifold, right? Into a multidimensional like boundary. It has to interpolate the space it hasn't seen. It has to kind of guess the bits for the examples that it hasn't yet seen. And so that's the kind of challenge there, is that, any model can theoretically have an adversarial input. It's just not clear, always what the application of that is or how resistant it is.
Yeah, I've seen some of those examples where like people like maybe paint their faces or things like this. I guess like Face ID is also response to that, because it also uses depth, right? I think like trying to like map your face in 3D, like with the points of that. You would have to like add appliances to your face to to fool it in some way.
Yeah, and the challenge is like obviously there's a kind of also a trade-off there in designing these systems, right? Because Apple were sort of in this situation with, once we all started wearing masks for COVID, well, that was a pretty like severe change to the way people were presenting their faces. They were having to pull masks down or remove sunglasses or all of those sorts of things, which are all affect the way the classifier works. And can you build a classifier that's robust to that, but still able to tell one human from another? It's not so clear, you know. That those are the challenges, the affordances in kind of real world ML design that you have to think about. Is like a more flexible model is both going to let in true positives and false positives more often.
Yeah, Face ID for me doesn't work with sunglasses, but works with my, glasses, just
really?
like normal glasses.
Oh, interesting. Yeah, no, I've never tried it with real glasses, but it definitely doesn't work for me with sunglasses on.
Which gets really annoying because you don't have you don't have Touch ID and it doesn't work. So you have to either take your glasses off and like put the phone in front of your face or like type the number. Like.
Right. Yeah. Since 2020, I have got a lot better at typing my passcode. I've got a lot quicker at that. But it was poor timing on their part to have a global pandemic just as they were releasing these things.
So what are some machine learning models or new architectures that excite you?
We're at a really interesting time in machine learning because there's been machine learning ideas for 70 years or so, or 80 years now. And, the first round, initially there was this kind of debate as to whether or not, machine learning models would be ones that we kind of hand program based on rule induction and based on kind of logic, or would they be based on this idea of kind of much more data driven and kind of mathematical modeling of the data. And so far, since 2010 or so, predominantly, I think the data-driven end of the spectrum has won. The other thing that kept happening was every couple of decades or so, there would be what was called an AI winter. So in particular, there was a huge one where what happened was there was a strong promise that, hey, machine learning is going to do everything, do all these amazing things. And there was a report that was submitted to the US government, which sort of said, hey, these things don't work nearly as well as we thought. The promise is not being realized. And it caused a huge reduction in the interest in research and industry in machine learning. And expert systems were a big thing at the time. A lot of the stuff that you see today, the use cases that you see today, the self-driving car, the automatic speech transcription, machine translation, and the digital doctor were all kind of, promised back then as well. And I think what's interesting is there was, for the first, I would say from 2010 to about 2015, I feel like we were all in the community kind of waiting for the next AI winter, for kind of the deep learning revolution to run out, for us to hit a wall, and for us to kind of say like, oh, well, we never got as far as we did. And, I'll leave it to your own judgment as to which of the applications have been successful and which ones have not. I mean, we don't exactly have self-driving cars yet, whether or not we ever will. But what we do have is a change now, which is that all of these architectures are coming with much more flexibility, much more reuse, and much more like capability. And we have a better methodology for deciding whether or not they work well. And I think those are things that have led us to a better thing. In terms of the specific, like, what are things that are interesting? Well, the deep learning revolution is everything, right? All of the models have been growing in size at an extraordinary rate. Specifically, transformer models have been the thing that I think for the last couple of years have really shown this really astonishing ability to perform at a level that I think is unexpected for most people. I thought they were cool the first time I saw them, but I never realized quite how like extraordinary they would be. And I certainly didn't realize that they were going to be the thing that sort of worked so generally and so widely in so many domains. And I think it's really exciting to see that sort of work going on so well.
How would you explain transformers?
So I think the best way to think about a transformer is that what a transformer does is it looks at a sequence of inputs, right? So the original models, these were like a set of words. And you have like a set of words in a sentence. And what you would do is you would learn the significance of each of those individual words by looking at all of the words that occur together over millions of sentences. And, by doing that over and over again, you kind of are able to infer this knowledge and compress the language into this set of parameters, this set of space, which sort of says, okay, well, there's this concept of chess, or this concept of Ireland, or this concept of cheese, or whatever word you want to pick. And those things kind of fit into this embedded space and the key thing is that it makes language differentiable. Because what was hard before was previous techniques and, techniques before the first work in this area of word embeddings, the difference between vision and we made more progress earlier in vision than we did in text is that you didn't really have this like continuous space of text. You have a continuous space in pixels, right? Pixels go from 0 to 255, right? They go from black to light, to white, and they go from black to red. You know what I mean? Each channel along the way.
There's a continuous path.
There's a continuous path. There's no continuous path between the word aardvark and the word zebra, right? It's arbitrary. Each word is somewhat related to another word, but not in this very clear fashion. And so that was always a challenge for us. We had a bunch of different techniques for this, and there's a whole pathway through work. Word2Vec was one of the early pieces of work on like learning how to do this thing of saying, okay, well, how do we learn which words associate with each other? How do humans learn about words? Well, they do the same thing. I learn a word by its use, right? And there's a thing called the distributional hypothesis. I like the phrase, words of a feather flock together, right? In other words, similar words with similar meaning appear in similar places.
Is that coming from words to an embedding? Is that what it's doing?
Yes.
Is that vector? Can you explain a bit more about that?
So the initial Word2Vec process was the first, I don't know if it was the first, but it was an early attempt to say, okay, if we think of language as the same thing, it's a continuous space. And in your head, you may visualize language this way. You may think, going back to our previous analogy, like cheddar and cheese are pretty closely associated words with each other. Smile and happy are pretty closely associated with each other. And that there's this sense that that words, while there isn't this direct continuous space, the concepts that they represent, the reference from the words, do sort of live together. And that words also, you can pick up their meaning from their usage, right? So you can understand some things about, if you say X is a large object, you might know you can infer some things about it. If you say X eats grass, you can probably infer a lot of things about it, this concept that it's probably an animal, that it's probably if it's large and it eats animal, it may be something like a cow. You can begin to think about all of those things. And if you say an X moos, you have a very strong sense of that,
So I've tried a pre-trained model from Google that does that. So you basically get like a sentence or a word and you pass it through the model and it gives you a tensor or like a vector, right? Like that Word2Vec. And if I don't remember wrong, there were like 30 or 50 digits, like floats. Like might be like -2, 1.3, 1.24, whatever, right? And as you're saying, what you notice is that if you put two sentences but just change one word, they're like, it changes slightly, but it doesn't change a lot. If you give it a completely new sentence, it changes completely. So maybe as a super simple example, if you thought of that vector just being XYZ, right? Like three numbers, 0, 0, 0. Maybe if you talk about I ate an apple, it's like 1, 0, 0. And if you say I ate a pear, it's like 1.200. Because it's like
absolutely
the same sentence change a bit. Just trying to...
Yeah. And I ate an apple, I ate a pear, but if you have on the other hand something like I picked an apple, you may not get the same, like it'll move in a different part of the space. And it's tricky, right? Because doing this is very hard because language is very sparse. We don't use all words equally. There's a small number of words that we use a huge amount. And then there's a large number of words, which are the most information-containing words that we use much more sparsely. So it's very difficult to learn this stuff. But the transformer essentially does the same thing. It looks across the sequence of words. It looks in this way, and it kind of learns these. It learns these values, and it does it what's interesting about it is that the structure for it uses this concept called attention, which is to look at the surrounding window of the words in this effective fashion. And transformers do a whole bunch of complicated things, but one of the key things is that we layer multiple layers of attention on top of each other, and we use multiple keys and values. So we store multiple simultaneous attentions. And what's really interesting about this, I was at a talk by one of the authors of the original Transformers paper, is he talked about this point, which is that, when, a lot of work tried to look at written word left to right for English, right? the way you would kind of mechanically read it. But the point was, actually, we don't think of sentences left to right. We think of sentences as complete blocks. And the best proof of that is these puns that depend on the last word, right? That change the meaning of the start of the sentence. Because you can do that, because you can update your understanding of the beginning of the sentence from the end of it, is a very clear indication that humans, you deserialize it, right? You kind of read the whole thing and then you understand the whole thing. The fact that we read it left to right is an artifact.
Isn't that also like what happens in German? So there's like a modifier at the end?
There can be. German has, because they have case endings, you can move the words around a lot more in German and play more word games, and Latin too, right? And so the more morphologically complicated your language, you can do more of these things. But the key point is that, like, we built a model that was able to do this. And in doing so, what we discovered was that this works on a whole bunch of other things. So these, like, learning these weights, learning these sequences of, so a transformer, because it looks at these kind of symbols together, what's interesting about it is that the fundamentals are very simple, right? This attention unit is a very simple concept. And so we can scale it very well. We can build very large networks of these and stack them very high. And it means that it can learn complex behavior from the different symbols inside it. What's nice about this is that it's allowed us to do two things. One is, it turns out that because this architecture is so flexible, you can train it using a bunch of different tasks at once. So you can say, okay, let's learn word prediction. One of the original high impact transformers was called BERT, bidirectional attention model, read from both ends effectively. And the thing that was interesting about BERT was they looked at two things. They said, guess the word. So they would give it a sentence and then mask a word at random and say, guess what word should go in there. And that was one of the tasks that the model was training. So recall with the Bayesian email, my task was, I'll show you an email body. Is this spam or ham? Now the task is, here's a sentence. Tell me what word is missing from it. And right or wrong over time, that was one of the things that it learned. And so being able to predict that word was a super powerful task.
Is that the first paper? Is that the first task that they trained it for?
So that was the way that they built the model. So what they've done is, before we had this idea of supervised training where you had to pre-label everything all the time. Now we're in a situation where we're moving away from just supervised learning, and we're doing two things. We're doing unsupervised learning, where we don't have this pre-labeled objective. Instead, we're learning the language first, and then we are going to be able to use that for something.
So GPT-3 is unsupervised?
GPT-3 is partially unsupervised. So they're all partially unsupervised in that
in what way?
So the way it works is that you set up a bunch of different tasks. So one of them is this word prediction. Another one that they used in the BERT paper was sentence prediction. So what they said was, do these two sentences come one after the other? So you might say, like, I got up early in the morning and I drank a cup of coffee. Those two sentences kind of follow on from each other. I got up in the morning and I fell out of an airplane doesn't make a lot of sense. And so those are the kind of objectives. And so training the model, I don't remember for the GPT-3 what the objectives were, but they have this unsupervised phase where the thing is really just learning language. You're trying to give it a bunch of ways in which to effectively learn language, guess words, understand the impact. And that combined with a relatively simple feature set and very, very large amounts of data and huge numbers of these transformer units gives you this surprisingly large behavior, this surprisingly emergent behavior about the system.
So what are some of the breakthroughs or tasks that language models are unveiling?
I mean, I think virtually all of the major NLP tasks are transformers dominate now. There are a handful that are not that case, but for many of the most important tasks, it's transformers are the dominant architecture for doing that.
What models were there before transformers for these tasks?
The most common one before was a thing called a recurrent neural network, an RNN. And in fact, that was where attention came from, attention was first attached to these RNNs. And there was a paper on, a lot of those came from machine translation. Machine translation is closely conditioned, right? The two sentences are parallel texts. So in other words, what's happening is I write a piece, I find a sentence in English and I find a sentence in Spanish, and I kind of line them up with each other, and I have a good chance with that. And, MT practitioners then relax all those constraints. They find loosely, they find non-parallel text. But recurrent neural networks basically would do this thing where the way they worked was they were that kind of thing of going one symbol at a time. They would go through, but each time they processed each symbol, they would remember not just what they'd done with this symbol, but the things before. And so they had this recurrent component to them, which allowed them to learn long-term features. And there's a whole set of architectures out there. There were long short-term memory architectures. There were gated recurrent units. But the key thing was, at some point someone said, hey, look, not only should we take account of the next symbol and the last one, but maybe we should add up the weights from all of a whole range of previous symbols and apply attention. And that's where that attention concept comes from. And it's this idea that like we should look across the symbols forwards and backwards as far as we can and maybe use that to help us.
So it never forgets.
So it learns to forget. That's the really interesting thing. With the LSTMs in particular, they have a thing called a forget gate. And the idea is like, because if you just learn everything, it doesn't learn. It's like the same as learning nothing, right? It's super connected. Everything is connected.
Copy paste.
Yeah, exactly. It's like making every noise at once, right? Or saying everything at once.
I was reading that the masking on the decoder, right? So this is an encoder-decoder network. The masking is actually what allowed to let the network not learn just the copy-paste task, but actually filling by the context of what it had learned, right?
Yeah, so you're right. There's this encoder-decoder structure. That's the other thing. So things go into this embedding space and they come out of it again. And depending on what task you want to do, you will decode things differently or encode things differently. And, what's intriguing about it is that, we began at a certain stage, you start to see these emergent behaviors. So the first thing that happened was we started to see that these transformer models were robust to a wide variety of tasks. So training this base model on a large data set and then using it in a supervised way outperformed just training from scratch. Then we started to learn that even larger models didn't really need to be trained that much or trained at all. They could do it from one or no examples. And that's why you hear this, especially with GPT-3, this concept of zero-shot learning. So in zero-shot learning, what I'm saying is, instead of me having to go back through this phase of here's 500 emails that are spam, 500 emails that are not spam, now I just say, show me emails that are spam. And the model knows the concept of spam. It has that spamminess concept in its embedding space, and it's able to effectively reason over that because of the complexity of the space. So that's what's happening at the like billions of parameters kind of scale, at the kind of hundreds of billions of parameter scale, of which GPT-3 and those are examples.
And it really feels like magic.
So there's two parts to it. One is it is very exciting as to see what some of the things it can do are. The other thing is it's very easy to get to fall into a trap to convince yourself of how good it is. And I think humans want to believe in it in some senses, right? There's a sort of attractiveness to it that means that you toy with it, you get more and more involved with it. It's very easy to lose yourself in thinking that it works in this very, very common way. And in fact, it is very limited in its boundaries. And that's true. I mean, it's surprising how true that is of very simple little models. Like you build little toy models and you're like, oh, this is the best thing ever, because you want it to win if it's your model or if you've been interacting with it a lot. There's a big affinity effect. And one of the challenges with machine learning is you need to be objective about the performance of things and understand what the scope and the impact of these things are. And like that can be very hard as the models get more complicated and richer. But yeah, I mean, they just in the last couple of days, I think it's yesterday or today, they released ChatGPT, which is GPT-3. And then they've done additional semi-supervised training on top of it towards dialogue. But people are having a lot of fun with it. So you can do things like ask it to explain Python algorithms. So one person did a thing where it was like, explain a Python algorithm or a piece of Python code for iterating through a list in the style of a 1940s gangster. So it does this very like 1940s gangster, kind of language that you'd imagine from like a Sam Spade movie or but it also pastes the code and it's all correct and coherent. Or what's interesting is it comes back to this idea that we have attention, right? One of the limitations of these models, or one of the things that's interesting about them, is those windows of attention are becoming the thing that we have to think about how wide it is, right? So the original BERT model could do between 128 and 500 words. Newer models can do more, but it's in its like bare form, attention is a quadratic growth. So it's very expensive to do more longer sequences. Now, there are ways around it. People have done all sorts of other things, but that context window in a zero-shot context is very important because you're providing all the information. It's the same as the frame of reference we have in this conversation. I can call back to a previous piece of the conversation. I can say, hey, remember when we talked about, your father's phone number? And you'll be like, yes, because we have a context window that is long, if you were paying attention. But if you weren't paying attention, you'd be like, what? I don't know what you're talking about. And same thing, the models forget over distance, or they attenuate over distance. So one of the interesting things that's happening now is how wide can we make these windows? What can we do to advance our understanding of the width of those windows? And what can we do to kind of learn over larger spaces?
I like that you said the concept of toy models and like playing with these things. I feel GPT-3, for example, like you can use it through the API of OpenAI. And it's really exploratory. And even if they told you how it works, let's say it's always going to be a black box model in some sense, because there's so much knowledge inside of it that you need to study what it's learned to know what it can do.
Yeah, and GPT-3 is a specific example because we really don't know what the model is because it's behind an API. And OpenAI are kind of misnamed, right? And there's always this joke that OpenAI is neither open nor AI, right? Kind of closed ML. And it's not clear, like we don't really know when you send a query to their model exactly what's coming back or what's going on. And in that sense, one of the things that you can do that's kind of neat, because these transformers are mathematically elegant. Getting there was hard, but the result is an elegantly simple thing. There are a bunch of people, 2 or 3 people out there who've produced libraries which are the simplest possible transformer and are like a very fundamental like toy transformer that you can actually use to learn how they work on very simple symbol sets. Now, you're not going to build GPT-3 with that, right? But what you can do is learn what a transformer does, how attention works, understand that fundamental principle. And a bit like kind of the toy, it really is a toy, but what it does is it gives you that fundamental understanding of what attention is, of how these models learn, what the propagations are, and what happens as you make them more complex. And I think that's one of the really interesting things that's going on.
I experimented with that by using GPT-3 and also DALL-E, like the image generation network. And both of them, in the different forms of APIs that they have, you even have to pay per image or pay per prompt, or like you have a set of credits that they're giving away on the beta for free. And you always have this feeling that you're like, you're being tested by the model. It's like, how good am I at making a prompt? So this gives me the thing that I want. Or is the model even going to know about the thing? Is it even capable of doing that, right? So every time you click, you get 4 images back on DALL-E, for example. And it feels really dumb when you get something like, okay, I added the cartoon word and I know that this makes the model make it so it's like hand-drawn instead of like 3D animation, a Pixar movie or something like that. And then you go and say, okay, I wasted that credit. This is not what I wanted. I'm going to edit that. Let's send it again. It gets, and then it's like you're building upon that. And the fact that it's behind a paywall or like behind an API that you have to be using credits, it restricts a bit the creativity. I also understand how heavy these models are, some of them, that they need to run in special infrastructure. So a really good move that is happening in AI these days is that they're finding ways to get these huge models into like compressed things that maybe are a bit less accurate, but it can run in like your own hardware or in less expensive machines.
So we very quickly hit this interesting point. Like the original Transformers paper was 2016. The BERT paper was 2018. And it's not in absolute terms a long time. But what was interesting was initially the challenge was that like you just needed any GPU, right? Like if you had a gaming PC, you could run these models. And that was true up until relatively recently. But, these kind of 100 billion parameter models are relatively difficult to run on your home machine without some transformation or some editing. But there was a brief period where it was really cool because, hobbyists or students with a reasonable degree of investment, and in particular, I'll say like a lot of the hardware companies were very good at like giving research research students free access or access. You could run these things. Now, I mean, it's more reasonable to offer these things to a wider audience through that, like that paywall or something, because now you don't have to learn to install it. But there is still a fully open track, right? People are building the open version of GPT, right? There's GPTJ, there's Bloom, which is the one that the Hugging Face organization has been, I think, sponsoring. Those are fully open and those are fully available. And I will say, like with Stability, they also Stable Diffusion is available to download. I mean, they've made their models available. They're pretty reasonable to learn. And in fact, it's been Apple today, for example, released the tools for converting your GPT for converting your Stable Diffusion model to Core ML, so that it will run on M1 architecture or M2 architecture relatively efficiently. So that stuff's available. So you are still seeing that, like, large companies are doing a lot to support people in this in a way that I think isn't very obvious in a lot of other places.
Can you comment a bit on the pricing, like how much it is to train Stable Diffusion? We did rough numbers yesterday.
Yeah, so Stable, I know for GPT-3, they spent, I think in the paper they talk about it being, I think it was $4 million it cost them to train their model. And I know that the previous generation of that GPT-2, someone was able to train that for $30,000. So you can see there's there's an upwards tick. I think I know I have no basis for what there was actually spent, but it certainly must be in the millions of dollars that it cost. I think we kind of ballparked it at about 800,000, but I have no basis for that other than kind of like looking at the numbers. Certainly what it did require was thousands of GPUs. So it's not the situation anymore where you can train this on your laptop or train this on your even a reasonably large cluster. You're going to need access to a HPC environment, whether that's a cloud provider or a university.
So that was 4,000 GPUs.
Yeah, I think it was 4,000 to A100 GPUs.
A100.
Yeah. In that ultra cluster configuration is what AWS called them. But yeah, so that's a lot of money, right? And it's a lot of resources. So, and the hosting of them is now not trivial either, right? Like the thing is, that's the other thing. You have to host these things on a GPU. That GPU has to, those cost money. They are resource intensive, There has been a lot of work actually in trying to calculate the CO2 equivalent of some of these training jobs. And, there's some controversy because, it's not obvious that it's as direct a thing as I use X kilowatts of power equals this amount of CO2 emissions, because data centers in particular have some efficiencies, and that calculating the real energy consumption in terms of those things is complicated. But it's an issue that I think arose first in the crypto in the criticisms of the crypto industry, but has also been leveled at people who do very large training jobs in machine learning as well.
What do you think the habit of open sourcing models and releasing maybe pre-trained models and papers, publications, what do you think that started? Because, there are companies, even like Apple, that would not publish any technical papers at all, and they've joined kind of that culture of publishing technical machine learning papers with contributions.
For the last decade or so, there's been this increased porosity between industry and academia, right? This genuinely, I think, of this larger crossover. There's also been a realization, I think, among many of the companies that to retain and attract the best talent, people need to be able to show their achievements to the scientific community, and everyone benefits. I think, the truth of the matter is that all of these large companies that release these things recoup multiples of their value and their investments in what gets done to their models, what gets learned, in the kind of community development. I think the other thing is the value of many of these models isn't the models themselves. It's how they get applied. It's the capability to be able to make those models, part of your business process, actualize them in those terms, right? So the transformer got applied. They had Google had a first mover advantage, right? They were using transformers in their translate and in their search results before anyone else really, I think, even knew what a transformer was. So I think they don't necessarily, so that they had an early advantage. And then other people have taken those forwards and done some exciting things with them, you know? So I think that's it. Like, you know, you could build the best transformer-based model in the world, but if you don't have anywhere to put it or any users to use it, why not release it, you know? I haven't stood back and had a really simple, like, clear narrative as to why, but I think it's an extraordinarily good thing that it has, you know, and like open science is the way
it's definitely accelerating.
we all win. Yeah.
I think it's definitely accelerating the pace of development. So I always had this feeling that in part it might be as a gesture of like, I did this first or something, you know?
Yeah. There's some element of that. I think there's some element of just like, hey, I think there is actually genuinely a sense of contributing good back to the world as well. Like these models facilitate phenomenal things. These models do allow people to do like really exciting stuff. And there is a strong sense. I thought the Stability CEO had an interesting point where he said, like, you know, there is a digital divide, and this does help with that, right? You know, like the number of countries in the world that contain companies that can train a $10 million training job is very small, right? I mean, a handful of European countries, the US, China, Japan, you know, not many more, right? I mean, your listeners will probably suggest others, but, you know, like it's certainly not every country in the world that can do this. And releasing these models lets people jump forward on that. You know, we've seen that in particular in the context of underrepresented or under-resourced languages. So back to machine translation as an application, transformers are robust in that area. They've helped a lot with those sorts of things of helping learn languages or preserve languages or translate between languages that otherwise haven't been, you know, heretofore been addressed in that way because they haven't been resourced.
What are some of the models that you've played with in the last years?
The whole BERT lineage is the kind of predominant model for a lot of the kind of classic kind of more business use cases, the things like supervised classification for entity detection, those sorts of things. So those would be, there was BERT originally, and then there's been a variety of other extensions to that, all kind of playing off that name. And I think that like Albert and Roberta are relatively recent ones that are kind of common. I don't do a lot of the generation side of things professionally because it's still rather uncontrolled. And the applications for it are still a little bit unclear for the type of work I do. But, you know, I've seen, for example, Jasper AI has been this company that's been exciting. They seem to be getting very far ahead with this idea of assisted writing. And I certainly benefit from seeing those models in my email client. Other models that I've looked at, I played with Stable Diffusion quite a bit because I think that's been an exciting model. It's been relatively easy to get running on a laptop. Increasingly, that's easy. I think, as I said, Apple have made that even easier as of today. Those would be the main ones, I think. You know, I've played a little bit with some of the more reinforcement type learning environments for kind of more toy implementations to kind of understand that. But, you know, the main one, I think, as I said, transformers are the place to be. So
what's the difference in the task or like how you train models with images with transformers compared to language models?
Except for the way in which you kind of feed the data in, which is not that complicated, I gather. I don't think there's a huge difference in terms of the architectures, right? It's not like, so with a text model, you have to tokenize it, right? Which is, there's this tool whereby you assign an index number to a word. That turns it into numbers, which you then leverage in the system. But I think my understanding is you don't have to do that because you have images already are numbers. They're just big matrix of like brightnesses. And so in that sense, it's much easier to go at it that way. You know?
So would it be more like a unit, like just convolutions and go to an embedding to the image or codings?
So they don't need to do convolutions.
Okay.
You know, a convolution was a way of doing the same thing, which was stepping across an image to reduce its dimensionality, reduce its resolution and highlight specific high points on it. Whereas the model, like with the transformers, you just give it a reduced size. It has to be a fixed size image. And back to that thing about quadratic attention growth, that's one of the limiters, is the size of the image input or output is limited. What's been interesting is that the way you fix that is you scale the image down, embed it, extract the output image, and then do a super resolution phase. So most of the models, what they do is they output a small image and then it's like the CSI zoom in kind of thing. It's that sort of experience where it then creates a larger image from that.
Yeah, with the difference that is real.
Oh, the difference that it's real. Well, no, it's not real. It hallucinates. So yeah. Like the difference is that it produces the results. But actually, very like that. It's not. It's it's not actually a photo.
If we go back to detail a bit more the tokens, right? Like tokenizing. Can you explain what that is?
Sure. So if you remember, I went back. We talked about this idea that like you need to try and figure out some way of making words, the space of language smooth and differentiable, or navigable. And architecturally, one of the things you need to do is the way we spell a word or the way we kind of compose a word of letters isn't really something that's very easy to use mathematically, right? Like it doesn't really give you a very natural matrix to work from. Some people worked on a letter basis. There were these character-based models, CAR RNNs, as they were called, which like looked at each letter number and looked one letter at a time. But one letter at a time, you lose a lot of context very quickly, and it's a struggle for the model to really learn words from that. So it has a very long way to go from those individual words or individual letters, because letters don't even represent sounds. They kind of represent parts of sounds very often. So an alternative is to look at whole words. And so the early work, the Word2Vec work, they looked at whole words, and you would just assign words. You could just say, okay, well, the first word I see in the corpus, I will assign letter 1 or number 0, and I will just, every word I see, each new word that I see as I go, I just give it a new number. So tokenizing is the task of splitting a sentence or a block of text, like a paragraph, into these individual words. There was another piece of work that said, actually, this is a problem because if there's a word that I have not seen before after I've trained, the model can't deal with it. It doesn't know what to do. These are called out of vocabulary words. And if you have an out of vocabulary word and you don't have some method to deal with it, well, you can say nothing about that word and you just have to ignore it. And that, as I said, because the less common words are often the most information carrying in the sentence, you're losing a lot of the semantic value of the sentence. So it turns out that what you can do is you can go halfway between characters and full word tokenization. And what you can do is you can split words up into, you can take the top 25,000 most common parts of words that you see. And it can be a complete word, or it can be half a word, or it can be a part of a word, or down to an individual letter. And every word can be decomposed into the largest subset of those things from your symbol tree. So if you have you're just going to take the. But if you have a word that you've never seen before, you're just going to give it each individual part. It may be 2 large parts or 1 small part. So like, let's imagine we've never seen automobile before. Well, we may have seen auto and we may have seen mobile. So we can use those parts of the words instead. And now we have a situation where the attention can be over those symbols and learn those symbol associations. And that helps us because if you remember, or if you think about it, sometimes we do that. We agglutinate words, or parts of words come together because they share meaning. Like there's this joke, I think, in linguistics that there's no such thing as a word, in the sense that like they are all composites of other things, or they all represent these like it's an arbitrary boundary of a thing. And so because sometimes words only make sense in word phrases in combination, sometimes parts of words make sense independently, and all that sort of stuff.
Yeah, that's a funny thing in terms of writing. Like when words are emerging, right? You use the dash.
Yeah.
Unless they're so widespread and understood that you remove them, right? Like a classic is email.
Yeah.
There was like capitalized E or lower E with like a dash and then mail. And then now we just write email.
Yeah, or ice cream.
Yeah. Ice cream was like that as well.
Yeah. And my favorite one is helicopter, because people split helicopter into heli and copter, but the correct is helico and pater, because it's that's the origin words are helico, and the PTER is like the start of pterodactyl. So like our intuitive tokenizers don't always work on the lineage of the language. But yeah, so then you have this table that allows you to kind of give the symbols. So the model really just sees 1 to 250,000 or whatever you have as your, or 25,000 as your structure, and that's the really purpose. So how you tokenize things can help you or hinder you to some extent, and then, but really all it's trying to do is find some robust way to represent like statistically significant combinations of symbols that it's going to see.
So we're talking about diffusion, right? And stable diffusion or imaging or DALI or all these models, right? There is like a starting part that is the text prompt, and then you go into generating an image, right? So as I've seen the architecture of Imagen, right? That I think it's more clear than DALI because DALI didn't have that diagram, but I guess that they're the same model. Well, not the same, but like similar architecture. There is this part where you go from word to an image, and then you do that upscaling that you mentioned, right? So what's the role of clip there in that part of the...
My understanding is this, right? So what you're trying to do is, remember we said we were learning an embedding space. So we were learning this idea that we were going to put words that were like each other near each other. We were going to put words that were not like each other away from each other. And we were going to say that they were kind of regions or vector directions that were going to represent similar concepts. So, you know, like you could sort of have this general sense that there's a region of animals, or there's a region of words that probably relate to the sea.
And when you're talking about region, this is like a highly dimensional space. It's like a
500 dimensional space.
It's like a latent space.
Yeah, it's a latent space. And
Okay.
the key point about it is that it's got this continuous kind of space to it. There was one of the interesting things they did with Word2Vec was you could build a translator with Word2Vec. And what you did was you basically just applied Word2Vec to English and then you applied Word2Vec to Vietnamese, monolingually in each context. And then you kind of looked at the resulting vector space. And what you discovered was that words that were similar to each other in the different languages would appear in similar spaces in the embedding space if you did it right. So you could kind of create this interlanguage space that was English-Vietnamese overlap. What was cool about that and what was interesting about that paper was that it preserved idiom. So you would have this situation where if you had a phrasing that was metaphorical or not indirect use of a term, but that like carried between the two, that would appear in both spaces and the model could handle that. Now that work was it was only good for the lab, right? It worked in kind of picked examples and it didn't work every time and it wasn't robust, but this intuition was interesting, which is we don't have to fill this embedding space only from one hose. So we don't have to like only pick English to fill this embedding space. We can build this embedding space and fit other things to it. So what you're doing with these multimodal tools, these like image and text things or sound and text, is you're saying, let's learn an embedding space that puts similar concepts from text and from image in similar regions. Now, doing that from scratch, every time you have to go from scratch, it's more expensive, it's more effortful, and it's more unpredictable. So what we can do is instead of doing that, maybe what we could do is say, okay, let's take a high quality map of English and map images onto it. Learn which parts of images or which regions of images are associated with different concepts over time. And that's what you're doing there, is you're kind of fitting your images to this embedding space defined by the language. That's cheaper because we have a high quality starting point. We're not starting from scratch. And, you know, we have these kind of concepts that are fairly robust. And so most of the models, my understanding of it is that's one of the reasons that you do that. So you can jointly train it. In other words, start from scratch with both and get to the end point. Or you can stage your learning in different ways, or there's all sorts of, I'm sure, detail to this that true practitioners are going to angrily shout at us about. But the point is that it's this intuition from these transformer models, which is starting from scratch is not the best place to do these things. Start from a rich model that, because it's a transformer, is a multitask model automatically, means that you can get to something where it will learn these embedding spaces effectively. And really that's what they're doing, right? There's a researcher from UIUC called Ted Underwood, who's a literary scholar and a digital humanities scholar and really a very insightful person. But he talked about the incredible nature of this, right? Which is that it's compressed virtually all of human language and symbolism into 2 gigabytes. You know, like it's really a very good expression of everything we taught in our language into this 2 gigabyte file, and then I can like pretty much extract whatever I want from it, real or otherwise. And that's kind of awe-inspiring, right? And it's a bit like the feeling I get when I look at Wikipedia, and I think there's a pretty good approximation of everything humans have learned, right? Well, even smaller than Wikipedia is everything humans can communicate in visual form and textual, and it's a couple of gigabytes of compressed weights. And that's kind of wild. And yes, it's imperfect. And yes, it's wildly narrow. And there's all sorts of caveats to that. But on a quintessential level, you're sort of saying it's kind of surprising how small this thing is and that it can fit like on a USB stick.
Plus, it can generate things, relations, so, right, like that generate relations between different concepts that don't exist, right? So it can interpolate, especially in the image space, because its pixels, as you said, are naturally continuous, and it can interpolate semantically as well, like maybe make sort of characters or objects or types of plants that don't exist.
Yeah. I mean, that interpolation, that intermediate space, that compressed space that is uncompressing, is very rich and astonishingly like powerful. It is, however, also full of spurious correlations. And I think we learned a lot about that in the language domain very early. We saw it early on, and I don't think the community caught up to it, but the ethics of machine learning is increasingly important. And it was not uncontroversial to release stability. It's a careful balance, because I think some of the fears are genuine, but probably based on an expectation of like performance that doesn't exist or capability that doesn't exist. But gendered language is a huge problem. Offensive language is a huge problem. Biased language under all the categories of like, I think it's fair to say the preponderance of human history has tilted heavily towards inequality, and that's reflected in the corpus. And so those sorts of things are things that we do need to address, because like, as someone said, like just taking the internet and turning it into a language model and then using that language model without really any guardrails is not going to produce something that's going to be like, I think, as bountiful as it could be or as pleasant as it could be.
It's already, it has a lot of biases, and from my reduced use of, for example, Stable Diffusion, some of the quotes, even though it has not safe for work filter, so that's NSFW, that prevents it from outputting certain images, I find it a bit disconcerting. Like if you write like a man with freckles or like a woman with freckles, I've seen it produce, like on the first test I did, like faces that were faces, but the freckles seem like it's half freckle, half like blood. So, it's like really weird, and you wouldn't expect that you can get surprised or like have that weird feeling about an image.
Yeah.
Right.
Yeah.
So, and I understand now the content filtering that OpenAI has been doing. It bothers you when you see just the filter and you don't see what's behind. But then when you actually see that some of those things are a bit gruesome, right? You understand why the filters are there in the first place.
I hear the argument where people say what real harm has been done or what real issue has been done. And, it's not completely invalid in the sense that I think people's imagination can get away from them. And I think there are people out there who benefit from overhyping ML or AI even, and the risks associated with it. So there is again always a balance to be reached here, but the fact that no one has been hurt by it is not an argument for not taking care of what's there. And it's sensible for the community to reflect on the ethics of this carefully beforehand.
Yeah, the internet is a bit wild. Like the first comments, like the top comments on Hacker News when DALL-E 2 was released and went viral, were like people asking like when somebody was going to retrain that to generate pornography.
Yeah.
Right? Like that's kind of the internet's first push always goes toward that. Like, so there's huge efforts.
Yeah.
And I've read that there is already communities that are training Stable Diffusion models to generate pornography, right?
Yeah.
It poses weird powers into the hands of certain people who are definitely going to use it for wrong
Well, it's interesting because, I think there's a sense that that kind of material has driven technological advancement or consumption of like widespread consumerization of technology. I mean, it certainly seems to have been one of the reasons that drove the internet to wider use, right? Itself. I've read, and I don't have, I certainly don't doubt that it was one of the reasons that particular formats of DVD or particular or the home video altogether was driven a lot. Consumption of that was driven a lot by these things. I think what's interesting is there is a shift now, right? Where before that was acknowledged or even kind of smirkingly looked at and, wasn't really discouraged. Now I feel like the community of technologists have taken a more clear stand that they want to avoid those tools being used for those things, right? That we're not going to use it to push the window of what's acceptable in the way that it had before. Whereas it was really, I think, encouraged or at least not discouraged before the kind of vice-driven uses of a new technology were allowed to let it propagate.
There is this possibility that you have the pre-trained model from Stable Diffusion. That means that one that they've trained for like thousands of GPU hours and costed a lot of money. You can relatively quickly, maybe in 30 minutes or an hour, you can retrain it or feed it new images and have the model now incorporate different images that didn't exist before and map those to specific tokens or special words, as they call them, I think. I don't know how they... But yeah, it's like we saw an example the other day that was arcane style, like the League of Legends TV show. And the model was retrained on arcane images, and you would activate that new class or style of images if you added or prepended arcane style to your prompt, right?
Yeah.
So can you comment? I don't know if you know the specificities of the filtering, but...
So remember the what we said before, which is that like these embedding spaces, these latent spaces, kind of collect together related concepts in the space. The other thing to remember is that the paradigm shift with transformers is now we don't just release the model. So in the past, like in the early days, it was like, oh, a new type of support vector machine comes out. The code you'd release or the code you'd write was purely the machine learning model code. And you would supply all your own data to get the result. With transformers, one of the major paradigm shifts is now we release a base model or a foundation model, or whatever terminology you prefer. And there are a number of ways that we can fine tune that model. So if I want to create a text classifier to come back to our spam versus ham example, what I will do is I will take that base model and I will supervise it. So I will teach it by showing it examples, just like I did our Bayesian classifier of 20 years ago. And it will use all the knowledge it has about latent language to be a much better spam classifier or more flexible spam classifier than the previous one. But that's a latent space. And we've also said, remember, that we can associate images. We don't have to just fill the bucket from one place. We can create this latent space. We can drop new concepts in. So if I want to do this kind of textual inversion thing, what I need to do is I need to create a region of this latent space that I'm going to define based on this new concept that I want to drop in. The high quality means they need to have something that is going to place them together in the region, in some region of the latent space, and then associate them with that keyword. But that's arbitrary, right? The keyword to image thing is completely like my choice. And then what I'm doing effectively is I'm saying, well, we already have this very well-formed latent space. So if I transfer these images in there, and then I drop this keyword on top of it, like basically if you imagine it, it's like all of these images come together as a glob, as a cluster, and then I give you the keyword that's the reference point to kind of put that blob of images in a particular space. Now I have added this concept to the knowledge space, and it's analogous to this idea that like if you're proficient in a language, you can learn a word from a few sentences. Children have to hear hundreds of hours of just to learn the kind of concepts of words. But, as you become more proficient in language, you become more able to just learn the concept of a word from its use. And that's exactly what's going on here is we have a developed latent space so we can insert these things in that fashion.
Going back to what you said before about the base model, I've seen now in the, in news blogs and things like this that talking about Stable Diffusion and other models refer to these as the pre-trained models, right? Like Stable Diffusion is pre-training. So Stability AI is pre-training Stable Diffusion with whatever type of model, right? So the pre-training now is referred to as the act of like this huge training of a base model or like a pre-trained model, as many times you can see. For example, in TensorFlow Hub, there are many of these, right? I specifically on the live stream, I did an example taking one of these language models from Google and retraining it really easily. I mean, following the tutorial, but retraining it to do sentiment analysis on IMDb reviews, right? And it surprisingly works pretty well. Like you can get to that task really well. So here the task is slightly different because you're like inputting images and like mapping them to a set of words instead of like mapping a review to a rating or something like that. Obvious thing is like because of the resources, right? Like you need thousands or millions of dollars to train some of these models, so like people can't really do that, but you can retrain and then
I mean, the other key thing about these transformers is that because they are these multitask learners, right? These very general ability to look at like sequences and arbitrary sequences of tokens together and understand that translation. They are very flexible in how they can be used for all sorts of other applications in that way. And I think that's a really strong factor to it. You might say something like, give me happy birthday, but jazzy at 250 BPM, and it'll do something like that. And I've never tried that prompt. So, if someone wants to try it and send it to us, we'd be happy to hear it.
So if you listen to that right now, is because we actually went on the website, generated that, and do that because it's going to be edited later.
And we apologize for your ears.
So the thing with Hugging Face spaces is that they also acquire this thing called G-Radio or Gradio.
Yeah.
And it's a visual interface. It's like just like HTML inputs and outputs, right? Like that you can see, but that actually allows them to host the model on their own servers. And through a UI, you can input the minimal input set that you need for a model, and you can try it on the web, which I think is surprising that they basically run all those inferences for free for whoever wants to try it. I mean, you can use Stable Diffusion for free in there. And if you go to OpenAI, if you use the API, it's like 2 cents per image.
Back to that question about why did these companies open these things up? It feels like to some extent because people like Hugging Face were producing these highly effective implementations of these models from, giving them away. Everyone sort of had to, right? Because it was going to happen anyway, so you might as well control it, right? Like the most popular implementation was not a Google or originated one in that sense, right? It was the Hugging Face.
I always find that when OpenAI releases a breakthrough model or some other people release these things, there's always somebody in like maybe 16 hours that has implemented the code in the paper, and they hit the front of Hacker News because, in Dali's release, the beta was closed and you only had like a landing page. But then after a few days, maybe you have like an open source implementation in Python or in TensorFlow or in PyTorch. And you get that.
People are there's a remarkable community of people out there. So there's an interesting, every time a new model comes out, there's an interesting race, right? There's the people out there to reproduce it. There's the people out there to kind of customize it. And there's the people out there who to kind of break it, right? And all three sets of people are out there. And I think like they each are contributing in a huge way to what we understand about what has been done and what is the consequence of what we've kind of created so far.
If we can go back once more, so it's clear for the audience and for me, can you define what textual inversion is?
Textual inversion is this idea that we want to insert a new word into our latent space and associate it with a specific set of images so that that keyword becomes part of the image to text latent space or text to image latent space that we have in our model. And so by leveraging that keyword, anything else we create can be done in that way. And the way the textual inversion process works is it's generally trying to add this concept in either as a style or as a, I think generally they work better to kind of make a stylistic thing. So like you said with the arcane thing, it creates everything you create with that keyword has that look of those 3D art kind of models. You can kind of make people look like they're from the cover of a Grand Theft Auto or something like that. It's that sort of stylistic thing is I think where it works best, rather than but you can use it to insert concepts as well, to insert like other things that it may not have seen before.
Yeah, you could insert an object,
you
like
can.
a new piece of furniture. You put a lot of images, and now you might be able to ask for that piece of furniture, but in a different material or a different
or drawn by the Simpsons artist.
These are all experiments that we need to try.
Yeah, I haven't done any textual inversion myself, so I don't know which things work well, and it's always unpredictable as to what will go in well and what won't, because it's down to very specific things about the model and the images. But certainly some people have done a fantastic job fine-tuning these things.
Yeah, so my intention, right? Spoiler alert, I don't know when this will be released, but my intention is to fine-tune it with my own sketches and explore like how it actually, if it actually works, if it does something that seems like my sketches, or if you can create other things in the style of the sketches. I've used previously like StyleGAN or Pix to Style to Pix, or Pix to Pix, things like this, but it seems like transformers are a game changer.
Yeah, no question. It'd be interesting to see, and it'd be interesting to see what you can do with that. You can output the latent space as well and plot the images and run tsne over that, or run UMAP over that, and try and get an understanding of what space you're creating in some senses, which might be fun to look at. The other thing that's interesting on the subject of text and transformers is that none of these models can read. Stable Diffusion 2.0 is interesting because they fixed one of the things that people talked about, which is the fact that it couldn't count fingers. So, a lot of the images that came out from the first version of the model had 6 fingers or 4 fingers, or were kind of, and that has a kind of a body horror aspect to it that's very wrong, But nonetheless, if you ask for a book cover, it'll have shapes that look a bit like language, but aren't like coherent text. And people have been interested to also look at the latent space from that. So I think it's Krungus was the word that people were using. And Krungus creates this like horrifying sort of Neanderthal, like a horror 70s movies, Hammer horror Neanderthal creature. And you could put Krungus in things, and you could, like, no one is, like, a Krungus isn't a thing, but the word appears in the space, and so interpolates to coherently this kind of monster, and it's very interesting to see what's come out. So people have been exploring this idea that, like, if you take the text that appears in those spaces, or if you try and unwind the latent textual space as well as the latent image space, you can find these ghosts in the machine, effectively, these kind of hallucinations of the model and hallucinations of the language that are very interesting.
Can you explain how would you do that? Go from the highly dimensional space in a model like Stable Diffusion into a lower dimensional space, maybe like 3 or 2 dimensions with tsne? Or
so for that task, you can get the model to output the raw. So that output from the encoder can just be the vectors of the things you've put in. So it'll tell you where each of the words you've inserted is, or what each of the images where you've inserted them fits in that space. And tsne or UMAP are dimensionality reduction algorithms that preserve different types of geometry or relative positioning. So humans can't visualize 512 or 1,000 dimensional space. It's beyond most people's perceptive power. But, and in fact, our intuition fails in those spaces. It's one of the nature of the curse of dimensionality. But these tools can reduce it down to a 2D or a 3D expression of some of the key structural features of proximity or relative positioning, or they preserve different things with different parameters, but you can basically use it to kind of it's a bit like a map versus the real world, right? Like a map doesn't preserve all the relative space, but it like, for example, the classic one is the globe projection, right? The Mercator projection distorts all of the sizes of things, but it doesn't distort the parallel lines across the horizontal. And that's the key point about it. And so similarly, this is a Mercator projection in some senses of this massively dimensional space. So it's not truly what the space looks like, but it gives you some sense of relative positioning of some things under these criteria. So it's a nice way to visualize things. You can sort of use it for getting a sense of stuff, but it's not like diagnostic or normative.
Okay. Yeah. So you will get the embedding of the prompt to get like the coordinates, let's say in 2D or 3D.
Yeah.
And then
you can just plot that normally.
Yeah, generate the image. I mean, you can plot the input, or you can also generate the resulting image of the diffusion and plot it there. So you can see the map
so you can
of
see
images.
where the two things go. That's right. Yeah. You can attach that as a label. And UMAP especially and TSNE they're pretty easy libraries to use if you're proficient in Python.
Okay. We'll put the links to all of these things on the show notes because we've mentioned a lot of technical terms. Some of them new for me as well. All right. So one thing I don't want to forget to ask you, do you have a mission or a contribution you want to do in this field? Like a overall contribution by working with machine learning and AI?
I don't have the talent or insight to be at the forefront of these things, but what I do think is important to me about it is I like the opportunity to make use of these technologies to kind of improve practical problems for people and address that sort of thing. So I get a lot of joy out of the application of this stuff, and I do actually also enjoy the process of kind of learning it for myself. So I don't have a grand scheme of contribution in some senses, but what I do think is that there's a community to be part of. There's a practice and use of things that allows people who don't have the same technical focus to get the benefit of it, that I think is a very valuable thing to do. And I think overall being able to share the knowledge is a great thing where it exists.
How do you stay on top of all the news and papers and new algorithms and models that are released?
What I do is there are a couple things. One is archive.org, which is the main place that most papers get placed in open source, in an open kind of context. They have RSS feeds, and you can attach your RSS reader to specific topics. So like there's a computer science language area and a computer science machine learning. That's a great place to get like breaking news on the papers level. There's a growing use of kind of social media for these things as well. Twitter has up until now been a very good place for these things. Mastodon is a growing area for these things. There's a thing called Sigmoid Social, which is one of the Mastodon, I don't know what you call them, Mastodon sites. That is kind of a place that a lot of, I think, ML practitioners and ML researchers are there. And then Discord is very popular. So many of the big projects now have a Discord. So there's a Midjourney Discord. There's a Stable Diffusion Discord, Stability Discord, and those sorts of things. So I think that's the other place to get a lot of this information.
Yeah, we also have a Discord on Getting Simple and the live stream. So we put things there, and mainly machine learning, the live stream and the podcast, and some of the things I publish online. What would be some advice for beginners?
A lot of beginners I meet are like, oh, I'm going to go from the basics all the way to the top. And you can do that, but it's going to be a long route. And I think you're, probably going to find it frustrating. Using the models as is, getting some understanding of which ones are interesting to you, getting to that point is probably the best way to approach these things. So, using, like, if you can iterate through, use the Dream Booth or the DALL-E or the OpenAI implementation, then maybe go get one of the like open source models and just reproduce that sort of a thing, and then play with that and kind of understand the differences between those. I think that, and maybe have a project in mind for those uses, is a better way to get to the place than trying to go from the like mathematical fundamentals up.
Yeah, I see 3 layers, right? Like there's the mathematics layer, the engineering layer, and the end user layer.
Yeah.
In mathematics, you want to understand like the equations and like the architecture of the models and like how to edit them or why one layer is put after the other and what they're doing. In engineering, it's all about, I'm just coding, so I'm creating an application, maybe use a pre-trained model, maybe fine-tune or train on my own data, but the architecture is like a black box to me because, you might understand it, but it's actually just something that somebody made and I'm using it.
Yeah.
And then the end user is like, okay, I'm just going to go log into openai.com or whatever site or huggingface.com spaces. And I'm just going to use the model, right? So those 3 layers, I think we all navigate between.
It's not linear is the key point, right? Because I think that's the challenge, is that it's, play with a model that you downloaded, go and read some papers on how it works, come back and play with the model again or play with a different model. Like bounce around, I think, is a much more effective way than trying to kind of linearly understand these things, because there just is a lot of trade-off and a lot, you just have to at some point kind of wave your hand over some part of it, because you either don't know it or it's too much to understand, and different people will find their different sweet spots there. But if you're very much a new beginner, start at the application end, start at that sort of end. The other thing is, I think it's you start to get a picture of how hard it is to get to the state of the art, like how far ahead the people in development of these things are from the people even kind of at the current edge. So getting to the point where you kind of have, especially if your objective is to do something new in this area, that is challenging, because getting to that state of the art can take years of work just to understand enough about the community to get there.
Do you have any book recommendations that have to do with AI and ML?
Chip Wen has a book on machine learning systems design that I think is a great book if you're trying to understand very much a practitioner's issue, which is, I want to build a machine learning model and make it work in production as a company or as a service provider. That I think that's a worthwhile book to read. In terms of like books on ML, my experience of them is that it's hard, because many of them, like the timing, the rate of like progress is so high that they tend to kind of become out of date, or kind of, it's hard for them to keep up. There are some very good tutorials and articles out there that I would recommend. So there's one which is the Illustrated Transformer, that kind of breaks down how BERT works in this very like intuitive way, explains everything about attention and the keys and all that sort of stuff. That's a great article. That's like a lasting contribution that I think I would recommend, and I think everyone would benefit from reading that. Now, other than that, I don't have a very strong, reading papers is where I get most of my information,
I just thought of distill.pub.
Yeah.
That was, I say was because, so that is a website that would take or maybe collaborate with breakthrough publications, and try to create a blog post, right? It's more like a visual essay explaining what the contribution is, and more importantly, with interactive components that would allow you to, I don't know, maybe move through latent space or see what each layer of a classification model has, or things like this. I believe, I might be wrong, but I believe that I read that because of the amount of work that it required them.
Yeah. They were works of art, but they were tremendously burdensome to
They
write.
stopped publishing them, but there are still a lot of them published and have like a really recognizable style that I feel like other people are also like using now for, it's just basically CSS to style the things, but it looks really crisp. And the other thing that I recently, I think it was like the 1st of November or something like this, Aurélien Geron published the 3rd edition of Hands-on Machine Learning with TensorFlow and Keras and Scikit-learn. I think I mixed the order of the title of the book, but it's the 3rd edition. And I think it would be super interesting because I have edition 2 and I can access edition 3 through O'Reilly online, but I don't really have access to the Kindle or the actual book. It would be super interesting if they released like a diff between the 2nd and the 3rd version.
Interesting.
Because the one that I noticed is that now you have a full section on the generative models for diffusion. Right?
Yeah.
And they have an example on the notebook. But other than that, you can't really get the diff of like, if you were to just read the diff, you'll say, okay, this is all that has happened between 2020 and 2022. And but yeah, there's like a lot of books. It's a bit overwhelming, books, papers, and things like that. So
I mean, learning to read papers is a skill, and spending time with papers is a good thing to do, right? I think that's something that, if you are interested in this sort of area, would be a wise thing to take some time at. And
it requires a lot of time.
It does, but you get better at it. That's the key thing. And like people who have done it a lot do it well. And actually, for a lot of major conferences, Open Review is the website where those conference papers get reviewed, and the analysis and discussion of those papers is often helpful in understanding what's going on. And it's not for everything, but that can be useful.
I'm enjoying a lot this conversation. I think we're going to have you more on the podcast. One thing that we mentioned, I have to kind of like scrap a lot of things that I wanted to talk about, but we didn't have the time because we just, I'm so interested in what we talked about and I'm learning a lot. So we'll spend hours. you mentioned this concept of the lab book or having a design document or like a writing document that helps you go through your assumptions and hypotheses while you're doing any type of work, any type of design experiment or work. Can you comment a bit more on the methodology or why you do it?
So this is definitely also one of those things where it's what they call a counsel of perfection, which is to say that I recommend this and I find it to be useful when I discipline myself to do it, but I'm not always the best practitioner of it on my own. I'm certainly no icon of productivity. Everyone will agree with that. But when I did my PhD, my supervisor, one of the things he talked about was the infinite fluidity of ideas, right? When you have something in your head, it just moves around and it kind of ideas are compliant. They will kind of fit you, whatever you really feel at the time. And your concept of what you're doing drifts in relation to your mood and your assumptions. And what happens is that you end up circling. One of the problems is you end up kind of going into rabbit holes or going around in circles because you're unmoored from any consistent requirements. So the practice here is to say, okay, well, first of all, anything we're doing is an experiment. So anything we're doing has a hypothesis associated. We believe we are going to assume some things. We are going to assign some things to error, which is to say we're going to say some things we just don't care about or don't know. And then we're going to have a hypothesis, a dependent and independent variables for the rest. And we're going to say changing our independent variables may or may not have an impact on our dependent variable. And, thinking in those terms about anything you do is helpful because then you can write in whatever format you like. Some people like long form, will write it as a page of text. Some people like a more, Excel style kind of bulleted list or some sort of other structure. How you decide to represent this probably reflects your memory palace or your visual or auditory kind of thought process. But the key point is you've written it down so that when you do something, you can come back and say, did the task I just completed agree with my assumptions and my error and my hypothesis? Did I actually ask the question that I was trying to test? And if it didn't, then I know I'm going the right way or the wrong way. And I can update my assumptions. But having it written down commits it in a way that no other way really does. And I think that's the core value of it. And, you can then look through it. If you're good at these things, you can keep a diachronic record of what your kind of ideas were and your assumptions were. And you can go back and think, oh, foolish me. I thought I could do this with, 5 images and I needed to do 1,500. Or, oh, I thought that, it would be easy to get this data out of these things. And that's one of the things you begin to learn is those things. But more importantly, you become metacognitively aware, which is you begin to be able to say, what are high value assumptions? What is a testable hypothesis that is in a sufficiently kind of coherent form that I can attack it? What is a item of work that is the sort of thing that's going to teach me something, and how do I analyze it? And that's the real skill of this, because strategy beats hard work, beats intelligence every time. But the reality is it is a tool that you become better at as well as you go on. And if you deliberately practice it, is part of the reflection on it at the in each stage. And by making it a piece of paper or it doesn't have to be, literal paper. It can be a notebook it can be a text file on a computer. You do have to go in and change that. And the discipline, you can also forget it. The way this fails is that you write these things and then you just throw them away or you never come back to them. And that is the kind of classic failure model for these. And I think that's a lot of productivity hacks. That's their failures. You don't revisit them. So you have to make it a habit to commit to updating it and treating it as a kind of an interlocutor in your process.
Yeah, so that's what I was going to refer to. There is a lot of power, and I've been thinking about this many months or years, the power of AI now into doing text summarization, highlighting, or keyword clustering or things like this, because I haven't been doing it specifically for experiments too much, right? I do write a bit about experiments in some forms, different forms. And I remember that I use a similar method to what you're saying, but not on purpose. It's just because I wanted to produce a text document. So for my master's thesis, you can see it at nono.mas/AI at the Harvard GSD Graduate School of Design with Panagiotis Michalatos. I made a point. I wanted to publish some sort of text document, right? I made it a visual essay on the web. So I'm sad that I didn't put the effort or the commitment to make formally publish a paper, because some people are citing it, but it's not a formal publication, right? But I really got a lot of positive development on the project by writing, and even going to a conceptual plane where you're trying to theorize why you're doing what you're doing, and then getting to a more pragmatic plane and trying to explain the technicalities of what you're doing. So going back to what you just said of revisiting, right, like what you've done or like forgetting about it, I actually have an episode on the podcast that is about my writing habits. I have this commitment, and for some listeners who've listened to previous episodes, you've heard this 1,000 times, but the habit I try to stick to, I did it right before you came for this podcast. I write at least 200 words every day, and I might describe like memorabilia, like just like memories of things that have happened, events. I mean, of course, on the plane, what did I do? I described the event that I lost my wallet, and now I'm going to update it with the fact that the airline has messaged me that they found it, right? So there is this thing of like recurrent practice on like documenting things. And I love the point that because I have the habit, I wrote it from the point of view of the person who's lost it and doesn't know if it's going to be found. And now I have that written. And now I update it from the point of view of, okay, this is what happened later. And my mindset is probably, the assumptions have been updated in my mind, but what I thought before is being recorded on paper, right? So I can go back and see what preconceptions I had or what did I think, because I actually described the possible things, the possible ways in which I probably lost it, and I was wrong, right? Like some of them were wrong. So I have some stuff written about this on the blog about how it's great to record your what you're thinking in the moment, because it will change, right? Like before you meet a person, if you describe what you think is going to happen, that you're going to forget, because your mind is going to mold what you think of that person as you get to know them. And I actually have this process, again, described on the podcast episode, that is auto-generating like a zine, right? Like a double-sided print with 4 pages per sheet. And I have a way to fold it and like staple it. So I have volumes. I'm up to like volume 86.
Oh my gosh.
And I try to do so. Every volume is like 7,000 words. So that's like 30 pages.
Is it handwritten or is it typed?
Some things I started like handwriting and transcribing with Google Transcribe. And I have been writing a bit by hand on the Remarkable tablet. So they transcribes automatically. And I do a lot on the phone or the computer that syncs.
I mean, have you fine-tuned your text generation model on that yet?
Not yet. So that is one of the things that, because I have like 770 mini essays of like 200 or like 100 words or to 1,000 words, that probably
it's probably enough to get something out of the model, do you know?
Yeah. So that is an experiment that I want to do. But the thing is, like, I do make this effort to print them physically, because it's rewarding as well to have an
tangible.
Artifact.
Yeah.
And I make a point to review them. And what I do is like I highlight things that you said, are actionable, or things that are maybe prompt for like a story, or like writing something that I can tell. And I always refer to that as the opportunity of reading what you write as a reader, not as a writer.
Mm-hmm.
Because, if you space yourself from something for like 2 or like 12 months, some of those things you might have forgotten that you wrote them. At the same time, you might go back to something you wrote like 4 years ago and say, wow, I wrote almost the same thing yesterday. I haven't been able to tackle this issue yet, because it's like a recurring thing that is really hard, and maybe I should work on that more, right?
Yeah.
So yeah, I don't know. I think it's super interesting method. I wanted to know about that, what your point of view is, and I might get to do that a bit more on the live stream, because the live stream I do mainly like creative machine intelligence experiments. A lot of it is like, oh, let's try to learn how to train this thing. Like one was like, let's train a stacked autoencoder and like use Disney to like plot my drawings. It didn't work quite well, but we plotted at least the MNIST data set, right? Like the fashion MNIST, Zalando's data set. But yeah, I mean, I think that that is great. And maybe in a future episode, we can talk more about academia and like
absolutely.
teaching and things like this that we didn't have the chance. But yeah, I hope that you enjoyed this.
Yes, thank you very much. It was a great conversation. It was really good. I really appreciate the taking the opportunity and your time. It was good, and hopefully your listeners will similarly be entertained.
Yeah, I'm sure. I mean, I've learned a lot. I'm actively trying to learn about all these concepts. I hope I can release this episode early because, if I release this in 4 months, it's going to be like...
everything's going to be out of date. It'll be like, those transformer things, what are those?
Yeah, thanks a lot for your time. I really appreciate it.
And thank you for inviting me.
We'll have you in the future.
I'd be very happy to.
Well, I hope you enjoyed this episode. Remember that you can find detailed episode notes at gettingsimple.com. And that you can submit questions about this or any previous episodes at gettingsimple.com/ask. This was one more episode of the Getting Simple podcast with me, Nono Martinez Alonso. Thanks a lot for watching. Thanks a lot for listening. We'll see you next time. Don't forget to like this video to support the podcast and to subscribe and click on the bell if you want to get notified when we publish new episodes or when I go live. Bye.